So one of the things I don't think I've said yet as we talk about climate changes is that I want you to know that as in this chapter we're talking about the climate changing, it's different than the day-to-day weather changing. So for instance, we kind of have an unusually warm start to our or end to our winter in 2012, but that doesn't mean that shouldn't really necessarily be associated with global warming. I think if you put this year's data in context of the last maybe 100 years and you look at the trend, then you can talk about climate change. So for instance, paleoclimatology looks at climate changes, but look, it looks at climate changes, how the Earth's climates have been changing over the last 2 million years. So kind of keep that in mind. Proxy data is data that we use to infer what climates used to be clear back way when. Now, the biggest thing about climate, as you might imagine, is we're talking about changes in the Earth's surface temperatures. Now, when we talk about surface temperatures, please know that we're not talking about like the rock and that sort of thing, the geosphere. We're talking about the Earth's atmosphere, about 5 feet above this Earth's surface is what we talk about when we're talking about surface temperatures. So proxy data is what we use to infer the changes. And I'll give you an example of studying proxy data to understand, in this case, what the temperatures have done for the last millions of years or so. So I've introduced a couple of new slides just to kind of clear up this idea about looking at oxygen. Now, oxygen has what paleoclimatologists do is they look at oxygen. Oxygen 16 is shown here, and it's a little bit lighter, and oxygen 18 is shown here. It's more rare. Oxygen 18 is more rare. And what paleoclimatologists do is look at what we say their relative abundance, or just how much of these isotopes there are in two things. Now, the two things we're going to look at are, I'm going to go ahead and I think draw a little, see if this will work. Whoa. Let me go ahead and draw a cloud. Okay. I'm going to go ahead and show it snowing. Okay. And from the snow actually is where we get these ice sheets. I'm having a hard time kind of spelling things, so I'm going to just put IS for ice sheets. Okay. Now, the snow obviously is made of water, H2O, and so each molecule of water has 2 hydrogens and 1 oxygen, and that oxygen can either be the oxygen 16 or the oxygen 18. Now, depending upon the temperature, for instance, if the temperature is cold, I'll just kind of start out with that scenario. If the temperature is cold, what happens then is that there is more of the lighter oxygen 16 here, okay? So what they have found is there will be more of that oxygen 16 deposited in the snow. Now it's the snow that makes the ice sheet. So then this ice sheet is heavy in oxygen 16. Meanwhile, below the ice sheet, of course, we have the ocean. Let me go ahead, and this is open ocean, and this is ocean under the ice sheet. And we have our little fishies swimming around in our ocean, or a little organism. And in the ocean, we have an abundance. If the atmosphere is cold, we have an extra dose of oxygen 18. Okay, the more rare of the 2 isotopes of oxygen. So the fish takes in the oxygen 18, and eventually it will die, and it falls to the ocean floor. And so the sediment down here is another thing that paleontologists get proxy data from. Sediment. Oh, sorry, boy. I know, I need to go find my pen. Okay, so that's the situation when we're in an ice age, basically, is we have more oxygen 16 in our ice sheets and more oxygen 18 in our sediment. So as we kind of talk about proxy data, I want you to know that their proxy data is coming from 2 sources. So this, if you're wanting to kind of go out on the internet and find this, an article that I kind of looked up to refresh on how this all works, NASA Earth Observatory, probably type in oxygen isotopes, That's how I found it. But what this is showing you is kind of what I suggested a minute ago, that the colder the temperatures, let's see, colder the temperatures, that's along the x-axis, so here's decreasing temperatures. Notice that the amount of that oxygen 18, that rare isotope, goes down. Okay, so that's why during ice ages, our ice sheets are deplete of oxygen 18. They have mostly oxygen 16. Okay, and then kind of related to that, you can think of it, is that the heavier oxygen, oxygen 18, and cold during ice ages is going to be in our oceans, and it can be ingested by animals, organisms that can go ahead and take it down to the ocean floor and add a layer to the ocean floor, a sediment that can be sampled then. Okay, here's just kind of another miscellaneous figure from that same website. So what I thought I would do, and again, I wish I had my pen, but I'm sure it will show up. I wanted to go ahead and just basically draw for you in contrast, looking at the proxy data from the ice sheet. So this is going to be my ice sheet again. Here is my ocean, okay, and we're going to go ahead and make this cold temperatures. So when it snows, okay, when it snows, basically, since it's so cold, like you saw a minute ago, there's not going to be much carbon 18, and it's going to be, oxygen. It's going to be an abundant oxygen 16. Okay, so oxygen 16 is going to stick with your ice sheet, and down here, your little fishies are going to be sucking in oxygen 18 in their water. And as they die, they create a layer. So that's in the sediment is oxygen 18. And if we contrast that to if the surface temperatures are warmer, let's go ahead. We still have an ice sheet. If the surface temperatures warm up, that ice sheet might be retreating. But here is the open water extending from that ice sheet. Of course, we have ocean underneath the ice sheet as well. Now our precipitation, when it falls as snow, since it's warmer, it will go ahead and have a fair bit of that less common oxygen 18. And so we will have oxygen 18 in our ice sheet. Now, if we go ahead and turn our attention to what's creating the ocean, the sediment in the ocean floor, our little fishy here is going to have a fair bit of oxygen 16. And so our sediment is going to be rich in oxygen 16. Okay, so if we go back to the slides that I had available for you, that's why, again, focusing on the seafloor sediment only. During ice ages, that we tend to have that oxygen 16 is kind of tied up in precipitation, creating our ice sheets. So oxygen 18 then is what we end up with in our sediment. Yeah, there you go. So, and I'm going to show you here in a minute a rig that basically cuts clear to the ocean floor and then takes a core of ocean floor out, a sediment, and draws it up. Then, of course, the sediment that's at the bottom will be the oldest, and the newest sediment would be the most recent. Or excuse me, the top sediment would be the most recent. So if you hit an ocean layer with a high amount of oxygen 18, then you would expect that suggests an ice age. So here's that rig I was telling you about. Kind of looks like an oil rig, doesn't it? So it goes out in the ocean and goes through the ocean floor and, goes through the ocean itself to the ocean floor and then drills down and pulls up a plug that that they can analyze. And among other things, they can test for they can search for oxygen 18. A lot of oxygen 18 means it was an ice age. So now switching gears, we're looking at the ice sheet. Now at the ice sheet, remember, it's different. So talking about taking ice cores, I always remember the movie The Day After Tomorrow, where kind of the opening scene are where those scientists are out getting ice cores. And so the deal here then is that if we see oxygen 18 in the ice core, part of the ice sheet, then we would imagine that suggests a warm period. So it's a different source of proxy data. Okay. So notice the other thing that we can do when we get ice cores is look for volcanic activity. And it's kind of cool, but we can, if they're careful, I should say they, paleoclimatologists can actually isolate the gases. And when they talk about the amount of carbon dioxide in the Earth's atmosphere way back when, what they've done is they've used these ice cores to carefully analyze for those trapped gases. Isn't that cool? So here is a guy working on a portion. I don't know if you can see this, but there's a cylinder here that he is cutting up. And so these are all ice core samples. Pretty cool. And here then is looking, using the oxygen 18 and the oxygen 16 analysis from ice cores to track what the temperatures have been like. Now, we're going to see a lot, or several different graphs in this chapter, and this is in units of thousands of years before the present. So let's see, this would be today. So, and this would be 5,000 years ago, 10,000 years ago, get it? And this would be 40,000 years ago. And so what you're looking at in general, this is Greenland, and it's looking at you can see how the temperatures are warm now, and they used to be colder, kind of going back. But timeline wise, I just think it's interesting. Where I kind of see the change is somewhere between 10,000 and 15,000 years ago. I kind of see this sort of change right there. Interesting.